So we've solved some axioms, and this is the scalar field that we've obtained. Now, what we did was a little bit unusual. Usually you wouldn't write down some logical conditions for some object to obey and try to solve those logical conditions. In physics, what we usually do is we write down some equation that, say, our field would obey. So does our field obey some equation that we could solve to get hold of it? That would be sort of the much more standard way of discussing this field. And I want to show you now that it does obey a field equation, okay? So what equation does our field obey? Well, I want to start off by taking a derivative with respect to time of our field 5x. Now, if I take a derivative with respect to time, where is that derivative going to act? Well, that derivative will act on the exponential e to the minus I k dot x and on the exponential e to the I k dot x. So to start, let's evaluate what is d by dt acting on e to the minus I k dot x. Well, this will be d by dt acting on e to the minus I omega kt plus I k dot x. And I have just used the expression for k dot x that I've got written just under the field. So if I take a derivative with respect to t, well, I'm differentiating an exponential. So I'll just bring down minus I omega k, and then I'll have the same exponential again, e to the minus I k dot x, okay? And if I take a second derivative with respect to t of the same exponential, this will just be minus I omega k squared, because each derivative brings down a factor, and minus I squared is a minus, and we've got omega k squared, e to the minus I k dot x. Do you remember what omega k was? So it was the square root of k dot k plus m squared. So we could actually write this as minus k dot k plus m squared e to the minus I k dot x. Good. Now, I want you to do an exercise. I want you to calculate what is the second derivative of e to the I k dot x. You're going to do it in exactly the same way. So pause the video and do the calculation. Okay, good. Did you do it? Well, I hope this is the answer that you got. Minus k dot k plus m squared e to the I k dot x. And you see, it looks exactly the same. Basically, for the first derivative, you would have gotten a different sign. But because the second derivative squares what you got, that difference in sign just doesn't matter. Very good. Now, let's calculate what is nabla acting on e to the minus I k dot x. Remember what nabla is? There is an x hat d by dx plus y hat d by dy plus z hat d by dz. And this will act on e to the minus I k dot x. Okay, so we'll have an x hat. And if we differentiate the k dot x, well, remember that, so let's even be a little bit more explicit with this formula over here. So k dot x is omega kt minus kx times by x minus ky times by y minus kz times by z. So if I differentiate k dot x with respect to x, I'm just going to get the minus kx. So taking the d by dx onto this exponential, well, okay, let's let's just be completely explicit, okay? This may be boring for some of you, but for some of you, it may be helpful. So let's just put it all out there. Okay, and now this is a very easy derivative to do. We're just differentiating exponentials. So we'll get an I x hat times by kx plus y hat times by ky plus z hat times by kz. And then we'll just have the exponential again, which is minus ik dot x. But this is nothing but I vector k, because we've got the x component of the vector times x hat, the y component of the vector times y hat, and the z component of the vector times z hat. So we just get e to the minus ik dot x. So we can now take a second derivative. If we take nabla dotted into nabla, so the Laplacian acting on e to the minus ik dot x, what do we get? Well, we will get ik from the first derivative, ik from the second derivative, dotted into each other, e to the minus ik dot x, and that is minus k dot k e to the minus ik dot x. Now, take a look. This is pretty interesting. When we took the second derivative, we had minus k dot k plus m squared e to the ik dot x. When we take the Laplacian, we get minus k dot k e to the minus ik dot x. So if we were to take d2, dt2 plus, sorry, not plus, I want to say minus the Laplacian onto e to the minus ik dot x. Well, you know what the second derivative with respect to t is? We just calculated it. You know what the Laplacian is? We just calculated it. So plug it in. We get minus m squared e to the minus ik dot x. Good. So what does that mean? In fact, these exponential factors obey this equation. E to the minus ik dot x is equal to 0. Great. Now, you should pause the video now. So don't pause yet. I want you to calculate this quantity. Do it in exactly the same way that we calculated things. Pause the video now and do it. Okay, did you get an answer? That's what you should have gotten. Very good. Okay, so now I would like to calculate d2, dt2 minus the Laplacian plus m squared acting on our field phi of x. And let's just put our field back in here. So our field phi of x will be an integral d3p over, we'll have 2 omega p, 2 pi cubed. So that's easy to remember. It's just the Lorentz invariant measure. Then we will have e to the minus ip dot x. We've got an alpha p plus e to the I p dot x alpha p dagger. Okay, if we go back up to the top, this is exactly what our field is. Just the integral over the Lorentz invariant measure, e to the minus I k dot x alpha k plus e to the I k dot x alpha k dagger. Okay, so that's exactly what I've written over here. Now, when these derivatives act, you know, those derivatives, the only place that they will act is on that exponential and that exponential, because there's no x and t dependence anywhere else. But we know what happens when those derivatives act on the exponentials. Those derivatives acting on the exponentials plus m squared simply gives us 0. So you can take this differential operator plus m squared through, you can have it acting on the two exponentials, and that lands up giving you 0. So what we've learned is our field does indeed obey the field equation. This is the field equation it obeys. And this is called the Klein-Gordon equation. Now, this was all about the t and x dependence in our operator, and also how it contracted with the p's, because we had omega p and spatial p appearing. So in fact, all of the x dependence and p dependence in our field, remember we fixed that before by the axioms which told us that our field was a scalar field. So how it transformed under Lorentz transformations. In fact, Lorentz transformations and translations. In fact, the Klein-Gordon equation is a Lorentz invariant equation and a translation invariant equation. So it's a Poincaré invariant equation. So now we're putting in that same content of how the field should transform, but we're putting it into the equation of motion. This is the Klein-Gordon equation. This is the equation that you would usually solve to get hold of a free scalar field.